Number 21, a coin is tossed 3 times. Okay, find the probability that you get 3 heads. This may not be so simple, and you may want to list all the ways that you get 3 times the coin toss. Well, the thing is, you have 3 coin tosses, and you have heads or tails on each. So there are totally, there are 8 total outcomes. What is the probability that you get 3 heads? Well, to get 3 heads, you just have to get head each time, and that's only 1 outcome, right? So the answer is simply 1/8. Okay. Now you could list all your possible outcomes. You can have 8, and you can do a tree diagram if you like. But it's pretty obvious that the only way you can finish this. There will be 8 branches here, but the only way to get 3 heads is this one out of the 8 possible outcomes. So you don't have to list all of these. You can just calculate the answer here. Number 22, you are to come up with a 3-letter code using alphabet letters, except you can't use Z. All right, so that means you have 24 available, 26 minus 1 is 25. So you have 25 available letters, and you are to use 3 of them. Well, you have to use you are to come up with a 3-letter personal code. Can you use the same letters again and again? Yeah, AAA is okay. X, T, X is also okay, right? S, S, W is okay. So you can repeat the same letter. There's nothing that says you cannot. How many 3-letter codes are possible? So you basically have 3-letter codes, 1 3-letter code like this. You have 25 different ways to pick the first one. Same for 25 for the second, and same for the third. That includes AAA and ZZZ. So the answer is 25 multiplied 3 times, and the answer is 15,625 different ways. Remember, the repetition is allowed, and order, of course, matters. Okay, number 23. The table below shows the number of kids at a certain school who can and cannot swim. Okay, boys and girls can swim, cannot swim. What is the probability that the child can swim? Okay, so this is regardless of whether they are boys or girls, right? So you look at the total column. You have 140 students, and out of them, how many of them can swim? I'm sorry, I shouldn't be looking at the last column. I should be looking at the last row, because this is can swim. 90 total children out of 140 can swim. So the answer is 9/14. If you want to calculate the percentage, you can do so. It's 64%, 64.3%. What is the probability that a child can swim given that the child is a boy? So at this point, all I'm worried about is this. Okay, I don't have to worry about all 140 of them. I only worry about the 60 boys. So out of the 60 boys, 40 can swim. That's 2/3, and that's 66.7%. Okay, so you can say that the 67.7% or 2/3 of the boys can swim. Okay, there is a little bit of disparity. If these are the true numbers, you can say that maybe the disproportionately more boys can swim as opposed to girls, or some statement like that. That's what these numbers are used for. This is called conditional, right? A conditional probability, where the first one is simply a probability. Number 24, complete the table below with the information given. Only 2% of the people have a certain type of cancer. Okay, so what is the thing that we use? The method is called a fictional 1,000 people table, or fictional 1,000 table. Out of 1,000 people, so this is where I will start. Okay, watch where I go next. Okay, now find out how many people will test positive, and so on. Only 2% of these 1,000 people will have a certain type of cancer, this particular cancer. So that's 20, right? And this is 20% of 1,000 people, because 2% will be I'm sorry, 10% will be 100, and 1% will be 10, and so 100%. I mean, 20. Did I say? I'm sorry, 2%. Okay, 2% of 1,000 is 20. Okay, so that is 20, and that means that you have 980. That's the rest of the people, right? In other words, 98% of 1,000 people would be 980 without that particular cancer. Now the lab test is 90% accurate on who has the cancer and who does not. So 90% of these 20 people, which is 18 people, will test positive correctly, and that means 2 unfortunate people will test negative, even though they actually do have that. That's called the false negative, right? These people think that they're fine because the test came out negative, but they indeed have the cancer. That's scary. These are the 2 very unfortunate people. We want to eliminate this number. That's very important in the medical field. But now focus your attention on the 980 people. 90% of those will test negative, okay? And if you calculate the 90% of the 980 is 882. Okay, so 882 people will test negative correctly, okay? And then the 10%, the other 10%, that's 98. 98 of these 980 people will test positive falsely, okay? So this is the false positive. These people actually don't have the cancer, but the test says it will. You do have cancer because the test is only 90% accurate. So 10% will be considered to have cancer when in reality they don't. Now let's add up each column. This is 116 here, 884, and of course this plus this is equal to 1,000. Now let's go ahead and answer the question, having filled all the boxes, right? Identifying who has a cancer and who does not. Out of the 1,000 people, find out how many people will test positive. So 900, no, I'm sorry. How many of them test positive? That's this. 116 will test positive out of the 1,000. And how many of them actually do have the cancer? Only 18 of them have cancer. Okay, so that these are the answers to the questions. Number 25. Oh, you can find the percentage here. 18 divided by 116 will give you the percentage of actual people with cancer among those who test positive, and that is a very low percent. It's going to be less than 20%. Number 25, to study which presidential candidate the California voters support. That's pretty obvious. A street interview was conducted in downtown LA and downtown San Francisco, because that's where you find a lot of people. What type of bias is present? Okay, what would you say to that? That's pretty obvious. Okay, so you may want to say something like the selection bias. The sample consists entirely of people in large cities. In fact, 2 large cities. Okay, rural Californians are not represented here. You can also call this location or geographical. Location, geographical bias or location bias. Typically, I mean, these are more specific types of bias as opposed to selection bias. Okay, so the last few questions will be on the next segment or the next part of this video.